Okay, welcome back to our second part of our briefing series this afternoon on Space Shuttle ascents and ascent aborts. And just to review, of course, this is in preparation for our simulator activities tomorrow. And Andy Foster is with us, who naturally those of you who have already been sitting here for the last hour know. And we're going to take this second part, which will be Space Shuttle ascent aborts. Andy?
Okay. Again, an ascent abort overview is why we're here. Let's press on to the first slide. Well, the intent of this briefing is to familiarize you with Space Shuttle intact abort modes. Okay, and just put a note up there. It's kind of saying if you haven't had the first briefing I just gave, you can watch this one all by itself, and it should make sense to you if you know something about ascent. But obviously, since machines are imperfect and break from time to time, we have to be prepared to deal with failures that may force us to do something other than we really want to do. Some of the examples of failures that we may have to cope with would be loss of a main engine, propellant system leaks, RCS or OHMs, major electrical system failures, loss of critical cooling on board the vehicle, or possibly cabin leaks. A series of intact aborts, and that means that we get the orbiter back in one piece, have been developed, and hopefully by using these intact aborts, and you should see not only the types that we use but how they overlap. We always give ourselves an out. If you ever have any experience with airplanes, you know that you always want to have an out, because the second you plan that you don't have one, or you try to push it a little too far, will be the second the machine's going to break on you, and now what do you do? Okay. So we're going to talk about the intact aborts and the types that we do, and I'm going to basically take them in order, more or less, or priority. In other words, for instance, the first one is abort to orbit. Well, out of all the intact aborts that we do, this is the one we'd really like to do first, because it gets us into orbit. And it's a lower orbit than the one that we really want. We always target for 105 nautical miles because it gives us a safe orbit. But it's still better than not getting into orbit at all. And it may become obvious to us early that this is the situation that we're in. So that's an abort to orbit. I'll show you that a little more in just a second. The next type of abort that we have is called an abort once around. What that basically means is that we don't quite make a full orbit for whatever reason. We take almost a full revolution around the Earth, and we return to a landing site. So in terms of like the ascent profile that we talked about, you'd have a nominal part of the ascent. You do an OHMS 1, but your OHMS 2 would be a deorbit burn, and I'll show you that in a little more detail. At one time I wrote this briefing up initially, landing sites were KSC Edwards and Northrop, and right now Edwards is our primary, and we use Northrop if we can't use Edwards for whatever reason. Next type of intact abort we're going to talk about are transatlantic aborts, or TALs. That's how you hear the crew refer to them. Basically, it's just a suborbital trajectory, almost a loft, a ballistic type trajectory, to land somewhere across the Atlantic. Most of our TAL sites are somewhere in Africa, and that has to do with where they are in relation to the plane that we go in orbit with. Yes, sir?
Just a quick point. At one point when you had an ATO, a lot of us were confused by exactly what you were aborting, since you went ahead and went to orbit. Could you explain that?
Well, if you think of it the way I think of it personally, it's an abort to orbit. In other words, when you're in an abort situation, I can't do what I want to. So an abort to orbit means I can't make the orbit I want, but I can still make orbit. So, you know, to me, an abort just means I can't do what I want to do. Now I've got to do something else. So when I take it in that context, then the terminology makes sense to me. I can't make the orbit I want, but I can make orbit. I'm just going to take this one at 105 because it's a safe one, and then we'll see what we can do from there. Does that help any?
So you're aborting checklist A and going to checklist B? So.
No, the procedures that we use are basically the same. Now, some flights, because of performance parameters, like 51F, for instance, which is where we had the ATO, some flights, we pick up ATO capability before we can go to our nominal orbit, which is Preston MECO. Okay. I don't know a real easy way to explain it, but it just means that the major reason we do that is that we're at a point in the flight trajectory where we can make it into orbit, but what we do is we dump OHMS propellant, burn it, both using the OHMS engines and the RCS. Okay. What that does is lighten the vehicle and improves our main engine performance enough where I can get to orbit. Okay. So what I'm basically saying to you is due to performance parameters on some flights, like if you, for instance, if I can get my Preston MECO point at 5 minutes, on some flights, if I dump OMS propellant, say, half my load, at 4 minutes and 30 seconds I can get to orbit. So you need some way to be able to dump that OMS propellant out. And I'll show you the abort rotary switch, and it has an ATO position. So the only thing currently that happens when the crew does an ATO abort and they push that button is they start dumping OMS propellant out of the vehicle, and it improves our performance to the point where we should make that 105 nautical mile orbit. All that's calculated pre-flight. In terms of procedures, in terms of what guidance is trying to do, it does exactly the same thing that it's going to try to do for a nominal orbit. Okay, it's not going to target for a different place in the sky now. There is capability to do that, and just as a point of reference, if and when we ever go back to WTR, you may see separate guidance targets for ATO and nominal. But most of right now flying from the Cape, that's not the case.
If I can
Okay.
remind all of y'all to wait for the microphone when we get around so we can preserve your questions for posterity on the tape.
Okay, I think we mentioned the towel. Let's go to the next slide. Okay, we also have something we call a late towel. And this is a towel that we basically do because of very last-minute system or performance problems that have developed. They're generally undertaken because we have a place in the flight profile where just on a performance standpoint we can still perform the towel, but because of maybe the way the guidance is designed in the software and so forth, if we tried to let the vehicle do it, it wouldn't do it for us correctly. So we actually have a manual procedure that we call a late towel that the crew could perform if we had a last-minute problem where we did not or could not get over to Edwards at least or go abort to orbit. Okay. The very last type of abort, and the one that you're going to see tomorrow, is the return to launch site abort. It's a flight profile undertaken when it is necessary to bring the orbiter home now. The towel takes roughly about 30 to 40 minutes to perform. An RTLS takes roughly about 22. So if our problems are such, either performance problems that I can't make a towel, or there's systems problems where I can't support even 30 to 40 minutes in flight, then this is the type of abort that you would see. Any questions over at least what types of aborts we do? Again, I'll go into these a little more in detail for you here shortly. Yes?
The launch site or one nearby, I'm just curious.
The reason that I use that phraseology was, again, it had to do with when we were looking at WTR, our Western Test Range flights out of Vandenberg. For instance, NAS Miramar was one of our return to launch sites, which obviously is not at Vandenberg. And Edwards Miramar was our second, I think, priority. Edwards was our first RTLS site. So, it would have gone back to Edwards rather than back to Vandenberg. At the Cape, it's KSC. We go straight back to the Cape. Yeah. Okay. Let's see now. Okay. We've talked about the intact aborts and what types there are. What I'd like to do now is give you the reasons, the basic reasons why we do these things. Why do we have to have these things available to us? Well, you can break the reasons that you do intact aborts down into two basic categories. The first one is performance losses. Loss of a main engine, for instance, would be a big performance loss. You could lose OMS propellant. That would be another performance loss. Or you may lose some type of system that's critical to you where you've got to get home now. Cooling, atmosphere, electricity, if it's bad enough, things like that. Now, how we determine what kind of abort we're going to do depends on several factors, mainly the timing and the severity of the failure. For instance, we usually design the flight profile to have one intact abort mode available to us at all times. So if we lose a main engine, for instance, could be anywhere within the first 4 minutes of flight, usually within about the first 2.5 minutes of flight. It'll probably mean an RTLS. But let's say if I lost a main engine now at, say, 5 or 6 minutes into the flight, well, now I may have the capability to go to orbit. So the point I'm getting at is, it's like I've lost a main engine in either case. But depending on when I lose that main engine, that may determine, or will determine, what kind of abort can I do. So the timing and severity of the failure is going to determine what kind of abort we decide to do. Yes?
Quick question. If you lost an engine, if you lost an engine in the first 4 minutes, You're saying probably an RTLS. What are the choices?
Well, the other choice is whether or not I have the capability to do a TAL on 2 engines.
And is that payload and everything else involved to make that decision?
Yeah, those numbers don't shift a lot from payload, and it also has to do with what kind of priority do I want to set. You know, is RTLS first priority or TAL? The way we're thinking right now, we'd rather do a TAL than an RTLS because it's less severe an abort than the RTLS is. So if we have TAL capability, we're going to do that. But there may be reasons why I can't support it, and now I've got to come back. But you have RTLS capability for about the first 4 minutes or so. Yes?
This list of abort procedures, does the difficulty and risk to the crew go up as you go down in the list? In other words, the least risky would be the abort to orbit, and the most risky would be return to landing site?
That's pretty well it. Mm-hmm. Yeah. Let's see. Okay. What I'd like to do now is let's step into each one of these aborts. Let's look at them in a little bit of detail. We talked about an abort to orbit, and again, we're trying to get to 105 nautical mile orbit. We've sustained a failure, but we can go uphill with it. Now, if we decide to do that, we can decide and select that thing pre-MECO. In other words, I can decide I'm going to do an ATO in powered flight. And I'll show you how the crew does that in a few minutes. They have a little switch that they can use. We also have the capability to decide that we need to do or will do an ATO after the main engine shut down. So we have a lot of flexibility there. All right. If we select it pre-MECO with this button that I'll show you in a few minutes, or switch, we will dump OMS propellant. I talked about this a little bit, through the OMS engines. Now when I say dump, I don't mean dump like airplanes dump gas. They just dump it. I mean, they open a valve and out it goes. When you hear the term dump, in terms of ascent aborts, what we're actually talking about is burning it through the engines. Now what we can do is we can hook up the propellant for the OMS engines. Let's use this in the OMS pods back here, and not only burn them through the OMS engines, but we can also burn them through these RCS jets because the propellants are common. Okay? And the reason, again, that we do that is basically by getting this propellant out of here, we're going to make the vehicle lighter, and it's going to make our main engine performance better. It's going to ensure that we get to that 105 nautical mile orbit. So if we do this pre-MECO selection with the abort rotary, like they did on 51F, boom, it's going to dump OMS propellant. Now it may or may not use OMS engines and RCS jets. That's really kind of flight dependent on whether they decide to do that or not. And the crew can also select whether or not they want to do that. Okay? Yes?
When you select abort RTLS, the dump starts immediately, correct?
That's correct.
But I'm not sure on how much you dump, depending on when the engine went down on you, or to a certain
No,
CG
it's a
or
timer.
what.
It's all pre-flight calculated, and it's a timer.
To set up a center of gravity for
Mm-hmm.
the
Pretty
landing.
much. I mean, you know if you dump that this is the CG you're going to have for the entry part and that kind of. Okay. All right. Yes.
I realize you're dumping mostly to lose weight, but is it also providing any thrust?
It will provide a little bit, but what you're talking about is most of it's from the OMS engines. It's 12,000 pounds of thrust on, well, it's not 4.5 million pounds at that point, but you know, it's several million pound vehicle, so there will be an effect, but it's going to be very, very small. Okay. Yes.
I'm just not clear on how much of this is automated and how much is done manually, depending on when and where it happens. Does the
Okay.
computer automatically read what has happened, and you just punch a button saying abort to orbit, and it does everything?
Right. It should. Right. The computers will basically, let's say if it's a main engine failure or a system problem, either one, they'll tell the crew you have a problem. And of course there are lots of ways it does that. Software displays, you'll hear tones, you'll see lights, you know, all the nice little things that you'd like to have. And it'll come up and say you've got a problem. And the crew assesses what the problem is. And then they will go in and select the abort. Okay, but after they do that, everything else should be automatic. Okay, may not be, but, and then they start, you know, taking action.
One simple little thing, you're off the pad and you drop an engine at 1 minute, but you got another minute on second stage with the solids. You don't select RTLS until you're off the solids, correct?
Actually, we wait until about 2 minutes and 30 seconds. The reason we do that is there is no scheduled guidance for RTLS until we get into second stage. The other thing that's going on in guidance is something called alpha limiting. because we want to keep a relatively stable attitude at SRB separation, it's not going to let the vehicle deviate very much from that attitude. So we don't really want to select before that, and basically what they did is they scheduled the guidance so that because of alpha limiting, it won't come in before 2:30 anyway. So both as a procedural backup to that software function, we just have the crew, okay, so if you need to select, you wait till 2:30 and then you abort. Okay.
Andy,
Let's see, Mark had his hand up for a minute, and then we'll come to Jim here. I'm sorry.
Yes, what happens if the computer system goes down while these other problems are going on? How does the crew know, and what do they start to do manually?
If your primary computer system goes down, you have no choice but to engage the backup, and that is through a push button on the rotational hand controllers that they would use if they had to manually fly the vehicle. The thing about the backup flight system is that once it takes command, A, you no longer have any other computer redundancy. That's it. And B, you're locked into it. In other words, guidance and everything in the BFS must be operating correctly because all the functions in it are automatic. There's no manual interface with it during RTLS until you get the tank off during a normal orbit, and basically any time until the main engine shut down. And then after that, the crew has to do almost everything manually. It's just, that's the way it's designed.
point of clarification, I'm assuming that when the dump is done, it's done just balls to the wall. The thing just goes open meter. There's no attempt to meter out the flow.
No, well, it doesn't meter out the flow per se. What it does do is monitor the amount of propellant that's being dumped, and it will automatically stop it when it reaches a certain level. We talked about I-loads. Well, the level that it dumps to is I-loaded. For some dumps, they're time dumps. In other words, it just comes up and times how long it's dumping. And it just depends on what kind of dump is being done.
But there's no attempt to preserve the equipment by metering the flow through.
Well, there's no need to,
Right.
to try to preserve the equipment that way.
Okay.
Yes.
Bill?
If you lost your engine or lost an engine at 1 minute into flight, you're saying that what would someone on the ground hear on the air-to-ground loop? Would they tell them RTLS at 2+30 or whatever you're saying the astronaut would?
Well, you probably won't hear that call until close to the abort select, more than likely.
Okay, so they would not rotate the switch until after 2+30 or whatever.
Well, as they come up on it.
Yeah, okay.
Yeah, okay. Yes.
Is there any situation where an abort mode would be triggered automatically, or does it always require that the crew punches a button in response to
No,
it?
it's not going to automatically take off and do anything. The crew has to tell it, this is what I want. Or if you don't, it's going to keep trying to do what it's trying to do, whether it can do it or not. So, if I could, let me press on here. And if you have questions on specific abort modes, I'd like to ask that you hold those until I get there. And that'll kind of keep my continuity going, and we'll press on a little faster. Okay, let's see, we talked about that. An ATO will require an OMS 1 and OMS 2. We're going in ATO because I'm losing performance, so I'm going to have an OMS 1 to help me out, okay? And we'll have a 105 nautical mile orbit when I finish. Any questions over ATO? Okay, let's have the next slide. And basically what I've done is just kind of have a little picture here for you to see an ATO. We looked at this earlier. The major point I'd like for you to get here is here was, for instance, the nominal orbit altitude. This is where I wanted to go. But I couldn't get there for performance loss, so I just accepted an orbit down here somewhere at 105 nautical miles. Okay? Now, we designed the ATO and AOA trajectory so they're very similar. And AOA will start out, at least initially, as an ATO. The OMS 1 burn for both are the same. All the procedures are the same. It isn't until OMS 2 where we get a difference, and I'll go into that in just a second or so. Okay? Yes? The 105 permits you to perform your OMS 2 burn. The OMS, Major Mode 104 software is set up to perform one OMS burn and is set up for OMS 1. If you tell it to perform one, whether you do or not, it will not perform OMS burns anymore. The other thing has to do with targets that come up, and 104 are going to be for OMS 1, and 105 they're going to come up for OMS 2. The other nice thing about Major Mode 105 is you can do multiple OMS burns if you needed to. Okay, so it's just a separate software mode with different functions. Yes.
Yeah. What is the vehicle's orbital lifetime at 105?
I believe that gives us 3 days.
3 days.
Yeah, that's what guarantees you. Okay. Any other questions? Okay, let's press. Wait a minute, I'm not sure that's right. Something tells me that's 24 hours, isn't it? Somebody back me up back there. Yeah, I was thinking 3 revs for 85, and it's one 24-hour period is what 105 gives you. Okay. Okay, we talked about an ATO. We're going to talk now about an abort once around. The only difference between the two, we start out just like we would for an ATO. We come up here, here's our MECO. We burn our OHMS 1 just like we would for an ATO. The difference comes in right here for OHMS 2. And now instead of burning to circularize, we turn the vehicle around, and we deorbit. In other words, I point the back end the way I'm going, fire the rocket engines, and I slow myself down so that I come back and perform an entry to our landing site. So that's an abort once around. Again, the only difference being that the OHMS 2 now is a deorbit burn. Okay. We cannot select an AOA pre-MECO. That decision usually isn't made until post-MECO, and even if it was, you'd basically try to go ATO and then just target your OHMS 2 for deorbit. Okay? Any questions there? Okay, next slide. Okay, you may hear some terminology which I'd like to go to here. I'll talk about in just a moment. There are actually 2 types of abort once arounds that we perform. If you want to call it a regular AOA, it's called an AOA steep. The second type of AOA you may hear referred to is an AOA shallow, and if you see a checklist entry, you'll see it designated like this, AOA-S. Okay. The difference between the two is only where the deorbit burn is performed. Okay. During an AOA steep, we perform the deorbit burn a little closer to the landing site than in a shallow. The descent trajectory is a little steeper. That uses a little more OHMS propellant, but in terms of thermal stresses on the vehicle, it's less severe. The AOA shallow uses less OHMS propellant than in a steep, but what we do is we use atmospheric friction to slow us down, to take off some of that velocity, and it imposes some very severe thermal stresses on the vehicle. Okay, so when would I use a steep and when would I use a shallow? A steep is basically going to be used anytime we're doing an AOA where we have OHMS propellant available to us to perform that. We're not going to go AOA shallow unless we have to. But if we've suffered, for instance, OHMS propellant leaks where we don't have enough fuel to perform the steep burn, then if we back that burn up and make our descent angle shallower and use the atmosphere to slow us down more, well, now we can use less OHMS propellant. We can guarantee that we still reach our landing site with that less propellant load. But the problem with it is, again, is that it does impose very severe stresses on the orbiter, and it's not something you really want to do unless you have to. Okay, so that's an AOA steep and an AOA shallow. Yes?
Is the issue with shallow reflight, or is there an issue of getting it done intact?
It's more of, am I going to be able to use the vehicle again?
Yeah.
There are some concerns with IMUs and whether they can hack a shallow and stuff, and that discussion is ongoing right now. Okay. Okay, once we do our deorbit burn, we're basically going to perform the same type of entry that we would during a nominal entry. We'll use OPS 1 software for the ascent and OPS 3, which is our entry software, for the entry part of the AOA. And just as an aside, this is also what you'd use during a nominal entry, is your OPS 3 software. And it will pick up with major mode 301. Just as an aside, 302 is your deorbit burn, 303 is a coast, and then 304 starts up with the aerodynamic phase, and there's 304 and 305. But any questions about that? Yes?
Could you tell us approximately over what part of the globe you would be on both of the steep and the shallow?
I'm not real sure, frankly, exactly where you'd perform the 2 deorbit burns. That's a function somewhat of the orbit and the amount of delta V, or in other words, the amount of propellant I've got to perform both of them. I'm sorry, I wish I could give you even a rough idea of where those burns are performed. I think I know where, but I'd rather not give you an answer that's wrong, so I won't say anything. Any other questions? Okay, let's go to the next slide. Okay, so that's an ATO and an AOA. So what we're going to do now is talk briefly about TALs. call them transatlantic aborts. They may also be called transoceanic aborts, but we'll call it this today. Transatlantic abort landing. It's an abort used when we don't have enough performance to achieve an orbit, or we've got to get the orbiter back right away. Okay? And as you can see, it's just basically a suborbital trajectory to the landing site, right here. So we just go uphill. We don't go quite as high as we do for a nominal trajectory. Shut our main engines down, get the tank off, flip the vehicle up, and then basically fly a nominal entry and land somewhere, usually in Africa. Okay, next slide. Now, the numbers that are here in this brief are, as you will see it in the software load, these are probably not the numbers that you're going to see when we fly again. And that there's a few reasons. I'd have to get into a lot of technical reasons why we changed it, but your main engine cutoff will occur at about 330,000 feet, inertial velocity of about 24,000 feet per second. Okay. When we fly again, the number is going to be up around 360,000 feet for the altitude. Just to give you an idea of it. Our normal main engine cutoff, I think, is like about 400,000 feet. So as you can see, you're considerably lower here. Okay. Once we take the tank off, we're going to pitch up to an angle of attack, or an alpha, of 40 degrees. So that means that the airflow, here's the orbiter, here's 0, and then we're going to pitch it up 40 degrees, and the airflow is going to hit it at a 40-degree angle. So we pitch it up to an alpha of 40 degree, and we make a normal entry to the landing site. Okay. Now, we talked earlier about late towels. You perform those when you've got to get the orbiter down, but the problem develops so late that either the software won't handle it very well, or, for instance, let's say we're going uphill and all 3 main engines shut off for whatever reason, and we're not expecting it. We don't have enough velocity to make an orbit. We don't have enough velocity to make it to Edwards. So the next thing they're going to do is look and see if they can perform a late towel. Okay. Basically, these do require, at least initially, some manual flying. It may require manual flying all the way to the ground, depending on what kind of energy state you have, where you are, and that kind of thing. Okay. And again, this is a manual procedure. It is in the checklist, and it has its own special little cards. Other than that, the trajectory is somewhat pretty close to a normal towel. It's just a suborbital type trajectory. Yes?
Is the manual need there because the velocity is just so fast, you're coming up on things too fast for the computers to process it?
There is there's a point in the software at about 19 or 20,000 feet per second, depending on whether 1, 2, or 3 engines are up. The auto software, simply with the guidance scheme that it has, really does a very poor job of getting you somewhere where you can perform a good